Yes, you can all see that. Great. Okay, so in the last class, we were talking about atomic scattering factors for the multi-electron atom. And this was a diagram that we used. And we got an equation of motion for each of the electrons, each electron labeled a subscript S. And we went through and we were able to calculate what the electric field would be that was seen by the observer. And this electric field, I don't have the final version of the equation, but this is what the equation for the electric field would have looked like to the observer, okay? Where the observer is seeing the summation of the field scattered by all of these different electrons. And this is the form that the electric field had, and we're gonna, okay, and it has a 1 over r dependence. It had this exponent, and I'll just show you an extra one step that wasn't in here, but which I want on a future slide, is that this r sub s and this exponent had this form to it. Did not expect it to remember that. But when you put this together, there's an omega out in front, there's a c in the bottom, and so that's a k, magnitude k, so which would be multiplying this. And this is the unit vector here. So k times the unit vector is k. So what we would find is that the observer sees this thing, but it has this very complicated phase thing. And this thing combined with this is going to give a k minus k incident. So because the waves are coming in at the incident wave is on an angle, the outgoing wave is towards the observer, there's a phase factor in here. And what we showed was that for some special directions, that term can go to 0. And it's important for us for today's lecture, which is refractive index. We're only interested in that special case, one of those special cases, which is when the incident wave, and you're only looking at forward scattering, okay? And by the way, as a reminder for me, rather than just electrons being little black dots, I have this electron wave function here with probability of where the particles are. And in this case, this is the quantum mechanical description of the electron dynamic. This whole wave function, combined wave function of all the electrons, is clearly a dynamical thing. And maybe the black dots are just the most probable place of finding them, but that would be moving also. Okay, so this is where we were yesterday, or Tuesday, and I modified the diagram just a little bit. I left out the incident vector, and I showed a new incident vector going in this direction. So k sub I is the vector, incident wave vector, magnitude 2 pi over lambda. This is lambda. The wave is coming in, and each of these electrons is scattering in all directions, but we're only interested in what goes in the forward direction because that's what leads to refractive index. Okay.
Professor?
Yeah, please. I'd like some feedback.
So
speak a little louder though.
Sorry, the quantity delta RS, so that's the displacement.
Delta Rx is measured from the nuclear center, right? And so each of the electrons is different, and this is dynamically moving around, and yeah.
Okay, great, thanks. Okay.
So if the wavelength were very long compared to the size of the atom, they would all see the same phase anyway. But I showed here purposely the case of an X-ray wavelength short enough that it's smaller than the atom, but and we're still going to get the refractive index to come out very simply, because as this wave front comes in, let's say compare the electric field seen by this electron and by this electron. So let's say when this one sees a certain phase, this one's going to not see it for some delayed time. And so there's going to be a phase shift in that sense of when they see the first peak, let's say, a certain peak, and then the wave moves along, and this one sees that same peak. So there's a difference in phase as the wave comes this way, but then on the emission, it's just the opposite. So this one starts earlier in oscillating, this one a little later in oscillating, but This one is closer to the observer by the same phase factor. So the phase of the radiation seen by the observer far away is unaffected by the positions of these electrons. Okay, and they simply, their differences in position don't add up to a phase difference here. There may be a phase because of the oscillation and resonances in that. It may be that there's a phase shift compared to the incident radiation, but they all will have the exact same phase shift. Okay, so is that hard to digest or overly simple to digest?
Professor?
Yeah, please.
I think to me, it conceptually makes sense. What I'm trying to conceptualize is like what magnitude of theta is small enough to be small, because it seems like for the wave propagation, you're comparing like the wavelength to the size or the distance from the nucleus. So that's like an easy ratio to think about, but I'm not sure.
Yeah, so the distance, let's just looking at the single atom, and we should look beyond that pretty soon, but the single atom has a radius, let's say twice the Bohr radius, right? So something like 10 to the minus 10 meters, and we're going to observe it in our refractive index measurement, I don't know, meters away on our beamline or something like that. So we're measuring refractive index as the wave goes through a physical material, and we're observing it at some distance. I think the angles are going to be small, but how small, we'll have a measure on the next slide. So it's a good question. Thanks, Lorena. Okay, yeah. So for me, this has become so obvious that I have a hard time explaining it now. So, but anyway, as the radiation comes through, let's say there is just not only within the atom, the positions of the electrons don't matter within the atom, but suppose there were other atoms nearby, much, what should I say, a millimeter away, a whole bunch of them. We're looking at, let's say, some thin film. Let's leave it that all the ions, all the atoms are the same. They're all cobalt or something like that. But there could be a whole bunch of them. And this wave, incident wave, I'm showing it as a sort of a plane wave, it wouldn't matter if there was another atom over here with its electrons also moving around. But it wouldn't even matter what the distance is between them, because again, the phases that reach the detector, the observer far away, or the detector or your sample far away, these things all cancel out. In the forward direction, the positions of the individual electrons simply don't make sense. So I'll leave you to swallow that, and we can come back and talk about it later, but let's see where this gets us. So the phase effect, what's happening is the atomic scattering factor has this phase factor in it. This delta K, this is from that vector scattering diagram. Delta K is K scattered, or K minus the K incident. So this is what's going to zero. So how far does it have to go to zero? Well, there's some estimate here. So I just put magnitudes on these things. Delta R magnitude being, for all of the different electrons, it's about the Bohr radius. It could be quite less than that, in fact. Okay, in inner electrons in a medium Z atom, their radii, their most likely position that they're going to be found in is quite a bit smaller than the Bohr radius, which is more associated with the outer electron. Okay, and the delta K comes from that vector scattering diagram, and it gets us this the factor, the 4 pi over lambda, and actually 2 pi over lambda, and the sine of the angle. So if you wanted to make some estimate on how small does that have to be, this is where you would go. Okay. And so this goes to zero or becomes extremely small, and I mean really small, in two cases. One is where the wavelength is large compared to the atom. So for the soft X-ray and EUV region, This is really small, okay? This is of order 10 to the minus 10 meters, and this could be nanometers or something like that. So it could be a big difference. And then there's the sign of the angle. And so for the hard X-rays, where this is not small, this could even be bigger, you know. Lambda could be less than A0, so this could be of order 20 or 40 or something like that. So we're going to need an angle that's less than 1 over 20 or 40, 1 over 20 over 40. Okay, so those two conditions are shown here: long wavelength limit and forward scattering limit. Okay, and when we are in that limit, this factor goes to 0 approximately, and we put a superscript 0 on here. And so that's my reminder. So that is not universal. Some people put it as a subscript, and then they put a 1 or a 2 for the real imaginary parts, or they'll put an I and a J. So, but anyway, for us, we'll recognize the 0. And I think you'll know now that for soft X-rays and EUV, for instance, in high harmonics and stuff like that, this approximation is going to work out fine because of the long wavelength limit. And in the X-ray region, it only works in the forward direction. If you're at any other angle, looking at hard X-ray scattering, it may be a factor. So, oh yeah. So this was our atomic scattering factor, and this is for an atom that's got Z electrons, and we're saying from S equals 1 to Z. So classically, where this developed in spectroscopy, they would put in an oscillator strength here. So this sum over S has the sense that, for instance, you could imagine some atom, it's got 2 electrons in the N equals 1 state, and they have an allowed resonance with some higher value of N beyond the other electrons, so into some unfilled state. And then, so that could be, the G sub S could be just accounting for those 2 electrons classically. And then maybe for electrons in the N equal 2 shell or subshells, you might have more electrons there, right? 8 electrons or something. So we introduced this. This is the way it was developed classically, with a so-called oscillator strength here. And in the early days, they were considered integers. How many electrons were in certain possible resonance, certain states that had certain whole units of oscillator strength. So, and these oscillator strengths are normalized to the total number of electrons Z. So I tell you that in a moment, or at the end of the lecture, I forget where it comes in, I'll show you what the quantum mechanical interpretation is of the same formula. And in the end, we wind up measuring them in the lab. So what we need is a proper interpretation. So I would say that this was an easy mathematical way to get the formula, which you wouldn't get from quantum mechanics, but it takes some little interpretation. Now we're going to go to refractive index. Refractive index be the ordinate here. 1 is the value in vacuum, and this is the values from the infrared to the visible ultraviolet X-ray region. And this is where we're going to see that we can write refractive index in a moment, with the atomic scattering factors appearing, the real and imaginary parts. And just in general, this is meant to look like in the visible, the refractive index would be about 1.5 for most wavelengths of glass. But notice the refractive index isn't the same for all wavelengths. So different wavelengths travel at different speeds. We call that dispersion. Dispersion is a phrase that means that different wavelengths travel at different speeds. And the formula, the mathematics that we're about to see, the refractive index does look like this. It's going to have more it's going to have more resonances than this simple diagram. But basically, there's going to be this business where it starts to go below 0, and for really hard X-rays, it stays below 0 and just goes over here. In the EUV, extreme ultraviolet, there'll be reasons here where it can go from 1 plus to 1 minus.
Professor,
Yeah, hi.
are those resonances medium dependent, or are those kind of like general?
Absolutely, they depend on the atoms that are there. So, for instance, if you have pick your atom, it's going to have K edges and L edges and M edges, like we spoke about before, and there's some substructure there which is not shown here. For instance, there isn't just a single L edge. There'll be all this substructure to it. Okay. So that would be, let's say, for cobalt. If you look at iron, there's slightly different. And if you have some molecules that you're looking at, some soft material that's got oxygen, nitrogen, hydrogen, and everything else, all those resonances are there, and you're going to need to combine the oscillator strengths for all of them. The oscillator strength is capturing as much as possible the refractive index or the scattering power, but not quite at the resonances. At the resonances, the formula doesn't work. Okay, it's just not complete enough. But at any rate, to answer your question, it changes for every different material because every material has different atoms in it. Okay, and thanks for the question too. Okay, so this is, we've seen this now so many times, and we haven't proven this, we haven't derived this yet, but we're about to. And this is what these two things look like. To answer Lauren's question, Lorena's question from last time, I don't know why this bump is up there. Why is that a little bit higher than the limiting value of 14? Got me thinking, but I don't know. And this is the absorptive part. And we'll talk at the end of this lecture, how do we find out these F1 and F2? But I wanted to bring it up here because of this issue about using the semi-classical model and then a quantum description interpretation of what the different parameters are and the performance. But the truth is, we can't calculate this. All the atoms we're largely interested in are just too complicated. There are just way too many different energy levels for all the different electrons that are there. And so we don't actually calculate it. What we do is we measure the absorptive part. That's relatively easy. Actually, the ALS is the place where the whole world goes for those atomic scattering factors. You know, you saw the website for Eric Gullickson. What they do there is they measure the absorptive part over as broad a region as they can. So they go down to 10 EV. And they measure that carefully, and they don't get all of the absorption edges. For certain elements, maybe for silicon or something like that, they may have more structure to it than this, but basically this is what you see. You know, there'll be many people at the ALS who are looking at near edge absorption structure, NEXAFs and XFs, to find out what does the structure really look like near these edges. But it's not captured in all these atomic scattering factors. So we get the broad brushstroke of this, of refractive index and scattering. We don't get all of the details. So people use synchrotrons to measure those further. Anyway, measure the absorptive part. That's like putting thin films of some material, and they always say in their natural state. So not just single atoms, but they'll put a thin film of silicon in this case and run radiation through it and vary the frequency of the photon energy and measure the absorption. And from that, they'll get F2. And then what they use is Kramers-Kronig mathematical relationships between the full spectral knowledge of absorption, and from that get a point-by-point analysis of the real part. It's not that you can't measure the real part, it's just extremely difficult to do it with accuracy. There is a few cases. There was a PhD thesis at the ALS some time ago, also working with Eric Gullickson, where they actually measured both the absorption and the refraction, but it is typically not what is done. Overwhelmingly, they measure absorption and then mathematically predict what it must have been here. So we'll come back to that, not a trivial issue. So now, okay, let's get on to what is this refractive index. So this is the wave equation, as we've seen, written in vacuum with some source of radiation where the current density J has this NQV. And in this case, we're interested in a lot of atoms, okay? And we're not interested in J scattering any place. We're only interested in J scattering in the forward direction, which is why we have this subscript 0 on it here. And so the current would be minus E N V. So here, the N now is the atomic density of all the atoms of a certain kind that are there, and you may have to sum over different elements there, and V sub S for the electron. So this is what we did in the previous lecture, and you could go back and check it, but everything else that you see here, this V sub S, this is the sum of this part, and it has a partial of E with respect to T. The velocity, you know, we had mass times acceleration, but the velocity here, I've written it slightly different this time, but I've written it, you can just check that when you look back for V sub S, this is what you'll find. And this was the partial with respect to time on J. So this partial with respect to T comes through here, okay? So maybe I didn't say that as clearly as I could, but this is just the forward scattering for the portion represented in this current density, which we would have had a charge minus E and V, and the V we would calculate dependent on all of these things, but the electric field, and we take a time derivative. So this is, I guess I didn't say that right. But anyway, this V sub S gets us this partial with respect to E with respect to T. So now we're going to put this current density in here. And it already has one partial with respect to T, and there's another here. So when we put this into the wave equation, the transverse wave equation, this is what we get. And we see that there's an operator here which has both the time squared derivative and the gradient derivative acting on the electric field. And then it has this source term for all the sources that are there. So this is what's different from vacuum. And it also has a partial with respect to E with respect to time squared. So this term and this term, this operator term on this, they can be combined. And this is just a repeat of the equation that was on the previous page. So we're going to combine this term and write it in this manner. So all of this now gets moved to the left-hand side, okay? And so it looks like this now. So here's the gradient operator that we had before. Here's the time operator, which had just the one part, that was the one, and it has this thing, which brought over to the other side is the minus sign. So now this is our wave equation in the medium. So this is describing some transverse electromagnetic wave that's going to propagate, and we'll make observations like we made before for simple vacuum. But this is in the form of a wave equation, and written in standard form, this is what it would look like, where there would be a phase velocity now, which would be C, the vacuum part, divided by the refractive index. That's how we define refractive index, by the way. It's the phase velocity divided by N, the refractive index. So all of this is going to come into the N, okay? And so if you just make the identity between this equation and this equation, you get that the refractive index here has all of these things. So this is the refractive index. So within the approximations which we made, which are good, this is what the refractive index looks like. And these frequencies are extremely high. This has units of frequency squared also. The plasma people in the class may recognize it. If this had been electron density, not atomic density, this would have been the plasma frequency. But even at densities of 10 to the 22, 24, the frequency here would be much less than this. So this square root of this is just going to become 1 minus a half of this. And now we've got our refractive index for EUV or X-rays. And maybe we should swallow it for a second, okay? So this is the atomic density. Usual parameters here. Sum over all of the atoms that are there and their resonances. This is some loss mechanism. Classically, it's absorption, something like that. It could be that or something else quantum mechanically. But we recognize these things, all of these things. We can rewrite this in terms of the atomic scattering factor. So this is just some algebra. You'll have to go back and check if you want. But basically, it is, okay? And now, because it was forward scattering, again, this works for any radiation, from infrared to hard X-rays further. And so these are our atomic scattering factors. Notice that there's a lambda squared dependence. If you remember that refractive index, when we showed it was n, it had all these, as we went towards shorter and shorter wavelengths, it gradually went down. There were resonances and everything, and it popped up, but it was always going down in amplitude, and that's the lambda squared. So while in the visible, this would have been one thing, in the X-ray region, this is going to be a lot shorter. So it's going, even without looking at these two factors, you already have a lambda squared dependence. So the refractive index is getting low. And this, we wind up writing this as, just in shorthand, 1 minus delta plus I beta. There's a minus and a minus, so that's a plus. And this should have a plus sign for the waves we've assumed. The plus sign assures us of absorption. What else should I tell you? Some comments or observations by anybody while we're looking at this? Okay, so we'll look at some of the limits on this, but this is our refractive index. What am I forgetting to say? Anyone want to pitch in with any comment?
Can I just confirm, you said that this applies to any type of radiation? That's because we're doing forward scattering where that theta is small and we don't have to worry about
Yes.
the
The
phasing.
analysis, right, that little semi-classical analysis we have was accurate enough. In the forward direction, this works, and it's good, right?
Got it.
So we have to put in some numbers here. All of these are natural constants. These things we have to measure. So we'll go into the lab and measure them, and then we'll have the delta and I beta. But
Thank
yes,
you.
yeah, and also I was thinking that I remember, learning these things as a student. I had a certain observation and that was that I would read something new and the first book and seemed okay, but some things I didn't quite get, didn't seem right. So I'd read the same material in a second book, and things would get a little clearer. And by the third book, the third book was always the magical book that explained it so perfectly. But I think in the end, it wouldn't have mattered which book I read in what order. It was just, it's helpful to read these in different books, I found. So towards that end, where did I looked today at two books. I looked at several books, but I have two of them here. One is Jackson's book. This is the third edition, which I forget if that's the latest one or not, probably is. But in Jackson, it's a reference for this chapter. You probably all know the book anyway, the library certainly has it. But in Jackson, it looks like where was I reading? Oh yeah, I was reading on page 309 in the third edition, and you'll see that same classical analysis. And he has interesting comments that he makes about it. And so if you wanted to just look someplace else, look Jackson, page 309. Another one, this is a book which is, what is it called? Yeah, it's from the Dover series, okay? And does it have the yeah, Grant Fowles. And it's one of my favorite books. It describes things in a different way, Maxwell's equations and propagation. It speaks about the polarization and that, but still it's the same kind of analysis. And in this one, I think if you went to page 155, so this is such a classic, the library has to have it, maybe the physics library, probably nobody's looked at it for 20 years. But if you just wanted to flip through a few pages in some other books, try Grant Fowles. It's one of the references in the chapter 3, and I'm looking at page 155. Okay, so some thoughts on that. So now for the quantum description. So this looks the same as what we had on the previous slide. Okay, this is the refractive index. And now we're talking about a quantum mechanical description with oscillator strengths, the G sub Kn. It's a double index. So these are now transition probabilities, and they're fractional. And these are transitions between any two states, a ground state and an excited state. And if you derive this to what degree you can quantum mechanically, this is what you'll get, okay? Where these oscillator strengths, again, add up to Z, okay? And this, the fact that they add up to Z is known as the Thomas-Reich-Kuhn summation rule. And this goes back to before quantum mechanics was known, just by spectroscopists, okay? And again, you can write this as we've written it before. And so you can see, oh, and rather than omega S, now you have all of these natural resonances between the two, the ground state and the excited states, and you have to sum over all of them, okay? So what does it say? Oh, at the bottom. Yeah, it gives references, one to Lieboff, which is an excellent book. It's an undergraduate quantum mechanics book, but it's a really good one. R.W. James, if anyone's really interested in hard x-rays, let's say for crystallography or anything else, R.W. James is the classic, and it gives pages where you can look up and see an interpretation like this. And this book by Corney is a really good, it's a quantum mechanical description of electromagnetic radiation, but it's a marvelous book, okay? But I think if you're ready to accept this, we're ready to go ahead, okay? Now, oh yeah, so we have been assuming waves of the following form, that our electromagnetic wave is propagating, let's say in vacuum, and it's coming towards some medium, and we've been writing it as e to the minus I omega t minus k dot r. In a one-dimensional case, this would just be magnitudes k times r, okay? But we've just found that while we would normally write, excuse me, just a second, we would normally write omega over k, omega is equal to kc. That's equal, that's the same as f lambda equals c, but we would normally have omega is equal to kc, but now it's c over n. So we can write this omega over k is equal to c over n, and then for n, let's put in our refractive index. And let's see how that affects the propagation of the wave. And so now we can solve for k, as shown here, okay? And we can take, so that what's fixed is omega. Omega is driving the waves, and the electric fields are oscillating. That's all with the frequency omega. The k sort of depends on if you're in vacuum or not in vacuum, in some medium, okay? But so, for instance, we have some wave propagating towards a material, and we come to the interface, everything on the vacuum side is e to the minus I omega t, and this will have some appropriate vacuum quantity, okay? But all the fields are oscillating at the same e to the minus omega t at the boundary. What goes into the boundary is going to have a different k, and that's what we're finding here. So this is going to be the k in the medium for a wave that's oscillating with a frequency omega, okay? So if we take this solution for k and put it up in here, just the one-dimensional version, this is what it looks like. So we have the front term, e to the minus I omega t, and then we have all of this stuff, omega over c times all of these things. If we multiply this out and combine terms, we'll see that the electric field has this amplitude, and it has the time dependence here, whoops, the omega term here, these two omega terms, there'll be a t, and this one will be an r. So this gets us the what do you call the retarded time. So this is the propagation that our wave would have in vacuum. But there are two other terms here, and one of them involves delta and one beta. So you just follow through the algebra here. This is what you get. You can take my word for it. And one depends on delta, the real part of the refractive index, and that just produces a phase shift. There's no this is not an amplitude term. This is an imaginary oscillating term. It's just that compared to vacuum, there's an additional phase shift now. And as we've seen, this could be negative or positive depending on where you are. And then this beta term comes out over here. And this is where you see that the plus I beta was necessary to get a minus sign here, okay? So this is your absorption or decay term, okay? And so from this, we can get what is the wave decay? In fact, if we square all of this to get intensities, we'll see that this beta will be related to mu, the mass absorption coefficient that we saw in the very first lecture, probably, okay? But this is a phase shift. So in the material, as this wave is now propagating in the material, it's no longer propagating just at the speed of light and vacuum, but there's a phase shift. So the wave is going either a little faster than that or a little slower than that, depending on delta. Which reminds me, I forgot to answer one question from before, but let me stick to this for a moment, okay? So here's what we just found, and this term is a phase shift term. So here's how you could in principle measure this. In fact, in the visible light and infrared, this is how you would measure it. But basically, you would make an interferometer here. So here's how an interferometer works. These are beam splitters, and these are mirrors. Your wave comes through here. Part of it is reflected, and part is transmitted. So here's a transmitted wave, hits a mirror, and comes down here, hits the beam splitter again. This part, the part that was reflected comes down, hits a mirror, and goes along. It goes through our sample. Our sample has a certain thickness, and it has a refractive index, which has these elements in it. So it's going to have a phase shift and a decay, okay? So the two waves get split and they come back, and this is another beam splitter. So this wave partially goes through, partially gets reflected, not shown. This one comes down, this one we're calling the reference wave because it didn't go through the object, and it comes down, partially reflected, partially goes through, not shown, okay? The two waves that got one reflected and one transmitted interfere with each other, and you can see a phase shift because of that. So for instance, if there's an object here which has a phase shift which depends, let's say, on position laterally, that's going to show up in the interference pattern here. And just to make this a little bit more real, here's the same diagram. Here's the object, and there's a change, what we call the fringe number, a shift in phase equal to an entire wavelength would be one fringe. So these are fringes. These are showing where the wave at different positions has gone through and has a phase that hasn't changed. So going this way, this would be bright, excuse me, I can't click, bright, dark, bright, dark, bright, dark in the regions away from the flame. By the way, this is a birthday candle flame. It'd be a few inches tall. And there's the wick. And then the candle is lit so that there's a hot region here. And because it's hot, it has a higher pressure. Pressure has to be in equilibrium all across the plane here. So if the temperature is higher here, the density is going to be lower. You know, pressure equals rho RT. So the temperature being higher, but the pressures are constant everywhere, this is going to be a lower density. The pressure is constant, the temperature is higher, the density is lower. So there's a refractive index change here just because the density changed. I'm sorry, there's not, the refractive index is what it is, but the density has changed. So I guess that's true, the refractive index has changed. And you can see this outlined in this candle. Okay, so anyway, this is measuring pure phase shift. There is, in this particular case, it's visible light. There's basically no absorption, very little absorption. Okay, so that was to explain what is delta. It's a phase shift. There's also the absorptive part. And the absorptive part we're used to. We talked about that. We just have to relate mu, the absorption coefficient. You know, we wrote that the intensity, there was an I0 e to the minus mu r. And that mu and the beta are going to be related. Okay, I wanted to mention also that what we've been talking about is a phase velocity. And for instance, let's just look at the darkest line here. The heaviest line, black line is going here. That's supposed to be one wave, one wavelength. You know, it's that's propagating along, and it has the crests move with a certain phase, and we call that the phase velocity. Okay, it's just telling us what are the peaks and crests moving at. Okay, and that's a monochromatic wave, and it only has one frequency, and it moves along. But there could be some other frequencies there also, which are, and this one is shown, the lighter black line is shown to have a slightly longer wavelength. And so it's monochromatic. It is at a different frequency, different wavelength, different frequency. So it feels a different refractive index. And that component of this wave packet, we'll call it, moves at a somewhat different frequency. And these two things, their peaks may add up here, but they may not add up someplace else. Here they're just canceling. And so there's this envelope of intensity, which it moves, okay? These waves are moving at, each wave is going at some fixed phase velocity. They're monochromatic, but the combination has an envelope which moves along, and it's different. The phase velocity can be, as we have seen, it can be greater than C or less than C, depending on refractive index, okay? And there's no problem with that. That doesn't violate anything because phase velocities are just monochromatic radiation, and they don't, because it's monochromatic, it doesn't carry energy, it doesn't carry information, anything. But the interference of several frequencies within an envelope, that does have a different velocity, and it's always less than C. So this is, we call that the group velocity, okay? The group of electrons within this wave packet. That's always less than C. The phase velocity can be more or less than C. So that usually requires some getting used to. Yeah, here's just another slide on the same thing. Here's a monochromatic wave propagating. The peaks and the valleys are going with a phase velocity, omega over k. That's what we found, okay? This phase velocity could be less than C, greater than C or less than C. It depends on the refractive index. But there's no energy or information transfer with this monochromatic wave. To get voice or send signals, you got to have some modulation. And once you do that, you're talking about group velocities. And the group velocities have a different frequency, a different dependence. It's the partial of omega with respect to k. In some cases, you'll find that the product is equal to c squared, like in certain plasma waves. That'll be the case when we get there. But anyway, I just wanted you to have this clear distinction in your minds that there is a phase velocity for monochromatic waves, and there is a group velocity. Okay? And this one is always less than c. Okay. This is the one where Einstein would tell you, don't exceed the speed of light. We're changing topics now. So before we change topics, were there any comments on this or questions? Or should I go back and ask about either this, just the forward scattering, the quantum description? These references here would be good for someone to look at. Yeah.
So the summation rule, which you mentioned here, so it's basically saying that like the maximum number of oscillators has to be equal to the number of electrons. I'm just having a little.
No, almost correct, but not quite. This is saying that there's an atom with Z different electrons, and every one of those electrons has some possible oscillator strength. Some are strong and some are not. And these are on average, they're going to give us what is the likelihood for a particular electron of all of those Z electrons in the atom. Let's just look at one for a moment. It has some probability of going to these in different transitions, okay? So that's for one electron, but there are other electrons and they have different possibilities. So there were a couple of these electrons would be in some initial state, but some others will be, like say a couple of them will be in the n=1 quantum state. A couple will be in the n=2, and that's got substructure to it, and n=3. And each of those, from each of those initial levels, has many choices of how to go in a transition to some upper levels, unoccupied upper levels. And so there's a transition probability that the atom would adjust itself in a quote transition. One of those electrons would have many choices, and these are all going to be fractions, small fractions, not unity, less than unity. Okay, and so for each electron, you have to add up all of the partials, and you have to add it up for all the different electrons. So you have to do, and these are written for as if it is the atom that's making the transition, right? We don't talk about the electron making a transition when we get a quantum mechanics. So this is adding up all the possible transitions of all the different electrons and all the different states that they might make a transition to. Okay?
Okay, thank you, that helps.
Professor?
Yeah.
On the slide with the like monochromatic wave and the phase and group velocity, I think you have an equation that says, the next slide, that says V phi times Vg equals C squared. But if Vg is always less than C, then how can this equation be true if V phi is not always greater than C?
Well,
like if they're both less than C, then I don't understand.
Oh yeah, no, that won't work. And this is not a general relationship. It works in some cases, but just in this case that you're asking about, for instance, the phase velocity could be 3 times C, and the group velocity would be, well, square roots. Let's make the phase velocity 4 times C, and this one would be, let's say, 1/4 C, the group velocity. So the phase velocity can be greater than C, right? For X-rays, they are. But anyway, so that's a little bit more. This is a little bit less. When we look at the plasmas, actually the variations are much larger, and we will see phase velocities that are quite enormous, okay? Much larger than C, and the group velocity will be proportionately less.
So this equation is only true in those 2 cases that are listed right below it.
I'm not sure how general it is, but it certainly includes those 2 cases. So when you look, for instance, even when you look for waves in a solid, you'll find not just X-rays, but there'll be other situations. And you'll get dispersion relations. I eliminated a slide here, but for instance, we've been talking about omega is equal to Kc, which would be omega squared is equal to k squared over c squared. But sometimes there'll be a second term in the dispersion relationship. We will find it in the plasma case, but I think in the solid state, you'll also find relationships like that. Anyway, not a general rule, but there are cases, okay? And it does give you the sense that when the phase velocity is greater than c, this is going to have to be less than c. Okay, good. Thank you for the question, the comment.
I have a question about the definition of a photon. I think I could be misremembering this, but I've heard that it is like a small packets of waves. And I've always kind of been confused because I know like light is a wave, waves tend to be continuous, but photons come in discrete energies.
Yeah.
And so, and now I'm just remembering my quantum mechanics. Wait, so would a photon be considered a wave packet like this, where we have multiple? No, because photons just have one.
Yeah.
Wavelength.
I think a photon would not be considered a wave packet because it's only one photon. A wave would have many photons, and a wave packet of different frequency would therefore have many photons, but some of them would be of different photon energies. That's probably a better way to say it.
Okay, yeah.
Yeah. Each wave has many photons, and a wave packet has a number of waves, slightly different wavelengths or photon energies. So it's going to have a lot of photons, but not all of the same photon energy. Okay, good. Okay. Anything else? Where are we on time? Okay, well, so now we want to use this refractive index. So for those who are interested in, who didn't take some electromagnetics class, we've developed a couple of things about scattering, Maxwell's equations, scattering, refractive index. Now we're going to use refractive index and find out what happens when radiation hits an interface. There'll be a reflection and a refracted wave in general. And how does that depend on the refractive index? And what we're going to do right now, I'll go over it, and you can read more in the book, where probably my language is more careful. I've had a chance to go over it. But this is just pure electromagnetics, which you could find in any undergraduate book of electromagnetics, either in physics or electrical engineering. But anyway, here we go. Here's our diagram. And this is, and I'm using the language and the letters that are almost always used. So there's an incident wave here, which is just shown as K, no I on it. Okay, it comes to an interface shown here, which is an interface between vacuum and some refractive index. We have a certain refractive index, but it could be anything here, okay? The fact that it's 1 minus delta has only one effect in this diagram, and that is the incident wave, rather than bend towards the normal as it would normally be for, let's say, glass, where refractive index was 1.5, the incident wave would produce a refracted wave, which was a little bit bent towards the normal, okay? And there's a reflected wave. And so we call the incident angle is phi, refracted angle phi prime, always measured from the normal. Phi double prime is the reflected wave, okay? And our incident wave in our normal form has this usual, some amplitude E0, and this is the phase variation, okay? Then there's a refracted wave and a reflected wave, and they all have the same frequency. You can just imagine right here, the incident wave is coming to this origin of our coordinate system, and it's oscillating up and down with some frequency, and it's driving the reflected wave, and it's driving the refracted wave, and they all have to have the same frequency. No getting around about it. But the propagation in the material or out here, that will depend on the refractive index, as we saw before, okay? So for instance, for the refracted wave shown here, has a slightly different amplitude, same frequency, but a wave vector that's different, K prime. And we're going to find out about these things. And then there's a reflected wave, okay? Has its own amplitude, same time dependence, but its propagation vector is this K double prime. All waves have the same frequency, and these two are propagating in vacuum. So the magnitude of K and K double prime has to be the same, and which is omega over C. So that's just an observation because they both have the same refractive index. This one doesn't have the same refractive index, so it could be different. Its magnitude could be different than the other two, okay? And what is this about the phase? Well, this is just about the phase velocities, okay? So for in this wave here, the K prime, the magnitude of this K vector is this, okay? Just go through some analysis. So that just sets up the problem. And one of the things that we'll find is, one is to calculate the amplitude of the waves on the inside. What are the electric fields and what are the magnetic fields and everything else? But some of the things that we'll find that are quite simple, if you say that your wave comes in and it somehow or other matches boundary conditions here, the electric fields are continuous, etc., and they're all at the same frequency, we're going to find out that if it meets the boundary condition here, because it's the same frequency, it has to meet the same boundary condition. It has to be continuous along. It has to always meet the boundary condition if it meets it anywhere. And from that simple observation, we're going to find out that the angle of incidence equals the angle of reflection, and the refractive angle is determined by what we call Snell's law. So let's see what's in the next slide. So these are the boundary conditions, which if we spent more time at this, these are learned from Maxwell's equations. What you learn is that the E and H components parallel to the interface must be continuous, which is mathematically written this way, and D and B components perpendicular to the interface have to be continuous. So we're not going to spend time on it, but if you apply those boundary conditions, you'll find that, for instance, the continuity of the parallel fields, whatever the field is on this side, just across that interface, as small a distance as you want, those parallel components have to be equal. They're equal at one point, but they have to be equal all along. And as a result, if you take the components of K along this axis, they just have to be equal. So the K incident, the K prime, and the K double prime, and that's what this statement is saying. Okay, so Kx and Kx prime and Kx double prime are all equal. The magnitudes in that direction, and it's just set by the fact that the electric field on one side, for instance, has to be, the parallel components have to be equal. And Kx, let's look at this one. Here's K, and this is an X direction is along the interface, Z is going in. So this is Kx, this would be Ky. So how does Kx relate to K prime in the X direction? Okay, well, they each have their angles. And so Kx is K sine of phi. And this one, along here, it's K prime sine of phi prime, and this one is K double prime sine of phi prime. And so just looking at the outer ones first, we observed before that the magnitude of K and K double prime, this one and this one, the magnitudes had to be the same because they're both propagating in vacuum, same refractive index, and they have the same frequency. So this K and this K double prime have to be equal. And if they're equal, that means the sine of phi and sine phi double prime. So the angle of incidence equals the angle of reflection. Okay, that's wonderful. Okay, in the same way, we can look at the X component of the refracted wave and the X component of the incident wave, this one and this one. They also have to be equal, and they have their own relationship from here. So it's just looking at these two. And when we do that, the K here is omega over C, and this K prime is omega prime divided not just by C, but C over N, written this way. But the frequencies are the exact same, okay? So as a result, from this relationship, we get that the sine of phi is equal to the refractive index in the upper medium times sine of phi prime. And this is Snell's law, okay? So the new angles, the refracted angle solved for here is the incident angle over n. And so normally this phi prime, there'll be some angle of incidence, and in a visible light, in glass again, refractive index would be greater than 1, and this phi prime would be smaller than phi. And therefore, the light would bend towards the normal, we would say, and it would be quite noticeable. And so that's what we see with prisms and light bending on, refracting at an interface with water. So just by the continuity of the parallel components of, let's say, the electric field, we get these relationships, okay, that for the angle of incidence equals angle of reflection, and Snell's law, okay? And we'll use these, and okay. And oh yeah, so we did this in the first lecture or two. We talked about, well, what happens from this Snell's law? I've just rewritten Snell's law here, but I've replaced n. I've left out the imaginary part and just put in, because it's mathematically difficult, but let's just say we're in a situation where beta is small. So this is Snell's law, and this is our diagram, but here we want to move away from measuring from the normal, because what we're interested in here is glancing incidence, and these angles are going to be very small. So the tradition is to measure angles from the horizontal. These two angles add up to 90 degrees. They're orthogonal, so it's going to make things easy. And this incident radiation, again, because this refractive index is 1 minus delta, this is going to bend towards away from the normal, okay? And this small angle we're calling theta. And what we're interested in is what happens if this is a normal, some small angle, but not so small, the light comes in and this bends away from the normal. This refracted wave is still propagating in the material, and it's likely going to experience a lot of absorption. What we're interested in is what happens when this incident ray, the angle theta, becomes a little bit smaller yet, and this ray, the refracted ray, is propagating right along the interface. So when phi prime equals 90 degrees, what's theta? What angle do we need? How small of an angle do we need to make this one 90 degrees where it'll run right along the interface? Because if it runs along the interface, it will have a lot less absorption. In fact, if we go a little bit smaller yet, the absorption of this wave will really disappear. And this is what we would call, is known as an evanescent wave. It's propagating along the interface, but the field into the material is exponentially decreasing. That's what's shown in this diagram here. So this angle we'll call the critical angle. When this angle is so small that phi prime is 90 degrees, that's what we call the critical ray here. This is the critical angle. And when it runs along the interface, the wave doesn't propagate, the refracted wave doesn't go into the material, it propagates along the interface. And if you make this a little bit smaller than the critical angle, the evanescent decay into the material is very quick. And absorption becomes very small, and you can wind up getting very close to 90-degree reflection, even for X-rays, which is really unusual, as we'll see in a moment. When you look at, we're going to calculate what it is at normal incidence. For instance, it's going to be 1 part in 10 to the watt, some really very, very small reflection. So let's just find out what is this critical angle for this refractive index here. So we want phi prime, the refracted wave, to be 90 degrees. So this is going to be 1. Sine of 90 degrees is 1. This is, when that happens, this is called the critical angle. It still has the 1 minus delta. but we don't want to work with phis, we want to work with thetas. So we're going to rewrite this equation here, as you see it, and we're going to replace phi by 90 minus theta. Okay, so this still looks the same. And the sine of this is the cosine of this. Okay, so that's you can just look up the trig or remember from high school. And so this is saying this is 1 minus delta, but we can, this is a small angle. We can do an expansion, and this would be 1 minus the angle squared over 2 plus blah, blah, blah. And there's a 1 on both sides, get rid of them. Then there's a minus sign on both sides, get rid of that. And then solve for theta, put the 2 on the other side, and you get that the critical angle is roughly the square root of 2 delta. So delta could be a number like 10 to the minus 3 or 10 to the, in the EUV, it'll be a number like 10 to the minus 2 or 3. In the soft X-rays, this is going to get much smaller. But let's say it was maybe 10 to the minus 4. So you take the square root and you've got a 10 to the minus 2. And this is in radians, okay? So this is how we're going to use mirrors to reflect at a high degree of reflectivity, okay? This is just a little bit more detail. We had some relationship for delta, so we could substitute it in here, and we'd get that the critical angle now looks like this. So we see that the critical angle gets smaller by lambda. This is square root and a lambda squared. So it gets smaller by lambda, and it depends on F1, okay? And so so here's the lambda factor. This is just a proportionality, but the F1 and certain wavelength regions, not always. This is a very complicated function of wavelength, but to some degree, it's at certain photon energy regions, it's approximately Z. So the critical angle depends on the wavelength and Z. So if you want to have a reasonable angle, you might use a gold mirror. So Z equals 74, that would make this angle sort of reasonable. If you try to do it with, let's say, boron or something like that, not so good. People like to do it with copper, but it turns out that copper is so soft, it's hard to polish. So there were certain materials that could use quite a bit, but this is how the critical angle goes. And we left out the imaginary part of the refractive index, but in real life, you're going to need to include it. This is a mathematical description showing what the reflectivity looks as a function of angle for different values of beta over delta. So this is just mathematical, no particular material. And you see it's very sharp when beta is 0. And if beta over delta is still small, well, you start to see a little rounding and a little rounding. But when it starts to approach 1 or anything close to that, it rounds off very much. So generally, you want to be in a situation where you get a relatively sharp angular cut. Okay, and here are some curves. These are calculated for carbon and aluminum, for instance, showing what kind of reflectivity you can get as a function of photon energy at the bottom. So this is 1,000 eV, 1 kilovolt, and this is 100 eV, okay? And this is showing different angles of incidence. And so for carbon at these angles, you can get a really good reflection coefficient. This is where the absorption edge is, okay? And so this is different from this calculation. This is using the real and imaginary parts of the atomic scattering factor. And here's aluminum, okay? Also looking really good. So this has a nice sharp cutoff. In astronomy, people use these to form images which block radiation, let's say larger than 1 kilovolt, just won't reflect off their mirrors, okay? So they know that they're looking below that, or they'll change the angle, okay? So they'll have mirrors at 2 different angles, okay? Aluminum is nice, but aluminum oxide may be what you've got. And so this is showing what the curves look like for when you have oxygen in there. And here are curves for gold. And so gold, you can see for 30 milliradians, you can still go out to several kilovolts and have a very sharp reflection. So we'll see about these being used. I'll show, they're used at beamlines at all the synchrotrons, but they're also used in all these orbiting X-ray telescopes. So like, you know, Hubble has been out there for years, but there's a new one going out soon. So here's an example of using those mirrors for imaging, just to capture the idea. But there are two curved mirrors. When they originally made, they were just cylinders, two cylinders at oriented at right angles. One is focusing in one direction, one focusing in the other direction. The first beamline at the ALS was the simplest beamline in the world. It used a KB pair, Kirkpatrick-Baez pair, with a multi-layer coating on each of them. And there were several different mirror pairs, so you could change what the coatings were. And what do I want to tell you about? So actually, that was the earliest ones. In fact, what you want are these things, you'd like them to be ellipses, in fact, ellipsoidal, okay, would be the best imaging. So an ellipse is point to point, but this has some off-axis radiation, so you'd need to have a little curvature the other way also. So the best performance would be with two ellipsoidal mirrors, and I'll show you an example. And it says these are commonly used in synchrotron and FEL beamlines, plasma diagnostics, astronomy. And these are shown with a magnification of roughly 1:1, but that's only to make a diagram. In many, many cases, you would have a magnification of, let's say, 100:1 or something like that. Is that where I wanted to go? Okay, so that was an example. What I wanted to do now was actually, before we just calculated what the angles were going to be. But now we want to find out, well, what is actually the reflection coefficient? If we have some wave coming in at a certain angle, let's say even normal incidence, where this one comes straight up here, the reflection is straight back, and the refracted wave is into the material, what are the reflected fields going to be? E double prime over E, and in fact, the reflectivity is the square. What's it going to be? And so we have these boundary conditions. And excuse me just a second. Yeah. So we have these boundary conditions on the electric field and the magnetic field, and we know relationships between the magnetic field and the electric field, so we can do it all in terms of the electric field. And we'll wind up, if we combine these, we'll wind up with 3 equations and 3 unknowns. So here's the one on the boundary condition on the electric field, boundary condition on the magnetic field, and then Snell's law. And if we combine those 3, we'll get these ratios. So this is the relative magnitude of the refracted wave and the relative magnitude of the reflected wave. And this is how they depend on the angles and the refractive index. Okay, and the reflectivity is a matter of intensity, not electric field. And so it's the magnitude of the pointing vectors, the intensities, like this. And so we have the ratio of the electric fields, and this is going to be what we call the reflectivity. And if you just look at this, this is the reflectivity here. This is what you get. It's this thing modulus squared. Okay, and this is just an N. It's a refractive index. So this could have been visible or infrared or even microwaves. Okay. And so anyway, we've obtained that for some refractive index. Now let's put in our refractive index. Oh, what did I do? Yeah, there are two polarization cases. So you usually treat them as orthogonal. One is where the incident field is perpendicular to the plane of incidence, and one where it's parallel to the plane of incidence. And so we showed you how to do the one. If you do the other, these are the results that you get. And the reflectivity for the parallel polarization is shown here. So they're slightly different. this is one, and this is the other, okay? So for instance, this doesn't have the n squared in front of it, and this one does, okay? So we're just going to look at normal incidence now. That's a sort of interesting case, in which case they're both going to be the same. They have to give the same result. But what happens if phi is equal to 0, okay? So this is going to go out, and square root is going to give an n, and this is what you're going to find. So for normal incidence, we could have started with either case. We're going to get the same explanation. This P means, S means it's normal incidence. It's that polarization. And this means that it's normal incidence. And this is what the formula looks like, but this is what it reduces to for normal incidence. And if we put in our refractive index for these n's, okay, one with a conjugate, this is the formula that you get. And these are both small. These are really small numbers, like 10 to the minus 3 or 10 to the minus 6. Even the imaginary parts are really small. So this is just a 2, and this is just a 2, or shown here. Up here, you have all of these things. If you multiply this out, there's a minus and a plus on the imaginary. So you get delta squared plus beta squared, and all of this doesn't matter. This is just going to be over 4. So the normal incidence reflectivity, delta squared plus beta squared over 4. So this is for all our EUV and X-ray wavelengths. We just need to go to the tables and look up, so that website, the CXRO website that Eric Gullickson runs, that you, I think, used for your first homeworks, find out what is delta and beta. And this is the reflectivity. So I put in some numbers here for nickel at 300 EV. This is the wavelength. There are tables in the back of the book. I put enough information in the tables that if you were on a desert island, you could still solve homework problems, okay? But looking up nickel at this wavelength, these are the values for F1 and F2, okay? And from that, this is what delta and beta are. So beta is like 10 to the minus 2 roughly. Beta is less than 10 to the minus 2. And the reflectivity is down below 10 to the minus 4. That's at 300 EV. And remember that these things go, there's a lambda squared in the reflectivity, and it comes as a square here. So if we did an example, and probably we'll make up a homework problem just using this formula for some different wavelengths, an EUV wavelength, a soft X-ray, and a hard X-ray, and just see how dramatically this number changes. So at 300 EV, there's a really small reflectivity. Okay, it's maybe a good place to stop. I think it's a good place to stop. I have to show you yet about Brewster's angle, but Brewster's angle for X-rays is pretty trivial, but maybe you don't know what Brewster's angle are. And there's the Kramers-Kronig. So I think we'll stop right where we are. So we found the refractive index, expressions for the refractive index in terms of the same atomic scattering factors. And now we've gotten glancing incidence reflectivity and normal incidence. And I want to quickly bounce back. You think of questions you want to ask. I want to bounce back. There was a question last time, and I saved it, the answer for now, but I forgot to say what it was. Yeah. So here we see that our refractive index, the real part of the refractive index, is proportional to F1 of 0. Okay. And somebody asked last time, what about the fact that F1 can go negative? And I saved it for here because here it's pretty clear what happens. When it goes negative, the refractive index becomes more than 1. So in the EUV, in the X-ray region, it doesn't happen. Okay, X-rays are always going to have refractive index, which is 1 minus something. But in the EUV, there are little variations here where you can cross over. Okay, and as you go to even lower energies, into this would be the ultraviolet right here, and into the visible, these values would actually be all on the negative side. Okay, so what does it mean that the oscillator strength here, not the oscillator, the atomic scattering factor is less than unity? It's negative. It means that there's a changeover of the refractive index, and the wave has gone from going faster than the speed of light in vacuum to actually slower than the speed of light, as is the case, for instance, again, visible light through glass. So any questions before we break? No. Okay. On the homework for tonight, I've mentioned to you about the equation sets that you can find them at the beginning of each chapter, but there's some cases after the book was published, I thought I should have put more formulas at the beginning of each chapter. And so I told you that I posted them at the B course site. There's a bunch of equations. And in doing these problems, most of it just comes from chapter 2, but you'll find some things in chapter 7. Whoops. And with that, I need to break. It is my faculty advisor who just turned 98. So I'll see you next time.
Thank you.